Decomposition of a square matrix. Hello everyone. To begin, let's briefly look back at our previous lessons, where we explored the definitions and properties of symmetric and skew-symmetric matrices. Now, there is a truly fascinating property in linear algebra that I want to introduce to you today. It turns out that any square matrix, regardless of its values, can actually be broken down into a combination of these two specific types of matrices. This mathematical process of splitting a matrix into these two distinct parts is known as the decomposition of a square matrix. In the upcoming slides, we will examine the fundamental theorem that allows this to happen, the logic behind the formula, and we will work through a step-by-step example to see exactly how it is done. Understanding the concept. Now that we have introduced the idea of decomposition, let's look at the core principle behind it. There is a fundamental theorem in linear algebra which states that any square matrix, which we will call matrix A, consisting of real entries, can be uniquely expressed as the sum of a symmetric matrix and a skew-symmetric matrix. To put this into a mathematical perspective, we use a specific formula. Matrix A equals 1/2 of the quantity A plus a transpose, added to 1/2 of the quantity A minus a transpose. To help you understand why this specific structure works, let us examine the two individual components of this equation. First, the term 1/2 of a plus a transpose is what we refer to as the symmetric part. Second, the term 1/2 of a minus a transpose is known as the skew-symmetric part. In the following slides, we will walk through the mathematical logic to prove why this addition returns us to the original matrix, and then we will apply this to a real-world example. The mathematical logic. Now that we have introduced the formula, let us examine the mathematical logic to see why it works. If we simplify the right-hand side of the equation we just discussed, we can see that it logically returns us to our original matrix. Looking at the first line of the derivation, we start with 1/2 of the quantity A plus a transpose, added to 1/2 of the quantity A minus a transpose. By factoring out the common term of 1/2, we can combine these into a single expression. 1/2 of the quantity A plus a transpose plus a minus A transpose. As we look at the next step, notice that the positive A transpose and the negative A transpose cancel each other out. This leaves us with two A's inside the parentheses, which simplifies the expression to 1/2 of 2A finally. Since 1/2 of 2A is simply A, the equation is balanced. This proves that the sum of these two specific matrices, the symmetric part and the skew-symmetric part, will always reconstruct the original matrix A with this logical foundation established. We can now move forward to a real-world analogy to better visualize this concept. Real-world analogy. Component analysis. You can think of this decomposition process as being very similar to component analysis in physics. For those of you who have studied vectors, you will remember that a single force acting at an angle can be broken down into two perpendicular parts, a horizontal component and a vertical component. In the exact same way, we are taking a single square matrix and decomposing it into two distinct parts, a symmetric component and a skew-symmetric component. To put this in simpler terms, the original matrix might be unbalanced because its elements across the diagonal do not mirror each other. By performing this decomposition, we are separating the balanced or mirrored part of the data, which is our symmetric matrix, from the antibalanced or inverted part, which is our skew-symmetric matrix. Now that we have established the mathematical logic and proven that the formula works, let us take a moment to visualize what is actually happening here through an analogy. Now that we have a conceptual understanding of this process, let us move forward and apply these formulas to a practical, step-by-step example. Step-by-step example. Now that we have established the theoretical foundation and the logic behind the decomposition, let us put these concepts into practice with a concrete example. Our objective here is to express a given square matrix, which we will call matrix A, as the sum of a symmetric matrix, P, and a skew-symmetric matrix, Q. Let us look at the specific matrix A provided on the slide. This is a 2 by 2 matrix, where the first row contains the elements 2 and 4, and the second row contains the elements 6 and 8. In the following slides, we will walk through the step-by-step process to find the symmetric and skew-symmetric components of this particular matrix. Step-by-step example Step 1. Now that we have defined our matrix A in the previous slide, we can begin the actual decomposition process. The first step is to find the transpose of the matrix, which we denote as a prime. To find the transpose, we simply swap the rows and columns of matrix A in practical terms. This means the elements of the first row will now become the first column, and the elements of the second row will become the second column. As you can see here, our resulting matrix, a prime, is a 2 by 2 matrix where the first row contains 2 and 6, and the second row contains 4 and 8. We will keep this transpose handy, as it is essential for the calculations we are about to perform in the next few slides to find the symmetric and skew-symmetric components. Step-by-step example Step 2. Now that we have found the transpose of matrix A in the previous step, let us move on to Step 2, where we calculate the symmetric part, which we will denote as matrix P. To find this, we use the formula. P equals 1/2 times the sum of matrix A and its transpose, A transpose. First, let us perform the addition inside the parentheses. We take matrix A, which consists of the elements 2, 4, 6, and 8, and add it to A transpose, which consists of 2, 6, 4, and 8. By adding the corresponding elements, we get a resulting matrix with the values 4, 10, 10, and 16. Next, we must multiply this resulting matrix by the scalar 1/2. When we multiply each element by 1/2, we arrive at matrix P, which contains the elements 2, 5, 5, and 8. As a quick check, you will notice that matrix P is indeed symmetric because its transpose is equal to itself. Now that we have successfully determined the symmetric component, we are ready to proceed to the next slide to calculate the skew-symmetric part. Step-by-step example Step 3. Now that we have successfully determined the symmetric part, let us proceed to calculate the skew-symmetric part, which we will denote as matrix Q. To do this, we use the formula where matrix Q equals 1/2 times the quantity of matrix A minus its transpose, matrix A prime. First, let us perform the subtraction within the parentheses. We take matrix A, which consists of the elements 2, 4, 6, and 8, and subtract matrix A prime, which consists of 2, 6, 4, and 8. By subtracting the corresponding elements, we get a resulting matrix with 0 in the top left, -2 in the top right, 2 in the bottom left, and 0 in the bottom right. Now we must multiply this resulting matrix by the scalar 1/2. When we multiply each element by 1/2, we find that matrix Q consists of 0, -1, 1, and 0. As a point of verification, notice that matrix Q is indeed skew-symmetric. This is evident because the elements along the main diagonal are all 0, and the transpose of matrix Q is equal to negative matrix Q. With both the symmetric and skew-symmetric parts now calculated, we are ready to verify if their sum brings us back to our original matrix. Step-by-step example Step 4. Now that we have derived both components, let us proceed to the final verification step to ensure our calculations are accurate. The goal here is to verify that the sum of the symmetric matrix, P, and the skew-symmetric matrix, Q, equals our original matrix, A. Let us perform the addition. We take matrix P, which consists of 2 and 5 in the first row and 5 and 8 in the second row, and add it to matrix Q, which consists of 0 and -1 in the first row and 1 and 0 in the second row. By adding the corresponding elements, we get 2 plus 0 in the top left position, 5 minus 1 in the top right, 5 plus 1 in the bottom left, and 8 plus 0 in the bottom right. This results in a matrix with 2 and 4 in the first row and 6 and 8 in the second row. As you can see, this is exactly our original matrix A. This confirms that our decomposition is successful. Now that we have seen the process in action, let us move forward to discuss some common pitfalls to avoid when performing these calculations. Common mistakes to avoid. First, be mindful of forgetting the scalar 1/2. A very frequent mistake is to simply calculate a plus A transpose and a minus A transpose and stop there. However, you must remember that the sum of these two expressions equals 2 times A. Rather than just A, therefore, it is essential to multiply both the symmetric and skew-symmetric parts by 1/2 to achieve the correct decomposition. Secondly, pay close attention to sign errors during subtraction. When you are calculating a minus A transpose, be extremely careful with your positive and negative signs. A common error is to subtract the elements incorrectly, which will result in a matrix that is not actually skew-symmetric, ultimately making your final verification fail. Finally, always check the diagonal elements of your skew-symmetric matrix, which we have labeled as Q. If you find any non-zero elements on the main diagonal of matrix Q, you can be certain that a calculation error has occurred. As a rule, the diagonal of a skew-symmetric matrix must always consist of zeros. Now that we have walked through a practical example and verified our results, let us discuss some common pitfalls to ensure you avoid these errors in your exams. By keeping these 3 points in mind, you can ensure your decompositions are accurate. Now, let us move to the final slide to summarize our key takeaways. Key takeaways. First, let's recap the fundamental theorem. Every square matrix can be uniquely expressed as the sum of two matrices, P and Q, where P is a symmetric matrix and Q is a skew-symmetric matrix. To find the symmetric component, P, remember the formula we used in our example. P equals 1/2 times the quantity of a plus a transpose. Similarly, to find the skew-symmetric component, Q, we use the formula. Q equals 1/2 times the quantity of a minus A transpose. Finally, as a best practice for your exams and assignments, always perform a final verification. Ensure that P transpose equals P, Q transpose equals negative Q, and most importantly, that the sum of P plus Q brings you back to your original matrix, A. If these 3 conditions are met, your decomposition is correct. Now that we have walked through the theory, the step-by-step example, and the common pitfalls to avoid, let us conclude with the key takeaways from this lesson.